Alright, welcome to video 2. Like I promised in the last video, we are going to take a look at how to simplify radicals, specifically square roots, in this video. So one thing that I kind of want to talk about before we get too far into the simplifying process is what does it mean to actually take a square root? We kind of talked about it in the last video, but you may or may not be familiar with what taking a square root actually means. So when you take a square root, what you're really asking is what number times itself will give you the number underneath the square root. So it's actually kind of the opposite, and actually is not just kind of the opposite, it is the opposite of squaring a number. So for example, if you take 3 squared, that's going to give you 9, because that is really saying you're doing 3 times 3 to get 9. And we talked about the exponent rules in lesson 1-3. If you take the square root of 9, that's asking what numbers do I multiply together to get a 9. And in that case, it would be 3 times 3. So what you will find is when you take the square root and when you take a square, those are inverse operations, just like multiplication and division or addition and subtraction. They're going to undo each other. So for example, if I took the square root of 3 squared, that's saying what number would I multiply together to get itself to get 3 squared. So if we simplified that, that would be the square root of 9, and of course the square root of 9 is 3. So really what we could have done as a shortcut is cancel those out, and we would have just gotten the 3. That works because those are inverse operations. And we're going to use that property as we go along the simplification process to help us out. So the first thing you're going to want to do is to complete a factor tree for the radicand. This is just like we started out doing in the prime factorization. We're going to take it a little bit differently, but you're going to start out with the exact same process. So we have the square root of 18 as our example, and we want to take that square root of 18, and we want to make a factor tree for 18. So we're looking for all the different numbers that we can multiply together to get 18. And choosing one pair of them to use. Again, just like when we were doing greatest common factor, there are multiple ways to do these. I would encourage you guys to look for kind of the bigger numbers that will go into things. It will work if you just do 2 for every even number, but it's probably going to take you a lot longer, especially if we get to some bigger numbers. So try and look for some numbers that are close together and that are a little bit larger than just your basic numbers. So for 18, I could do 2 and 9. Or I could do 3 and 6. I'm going to go ahead and do 3 and 6. Now again, 3 doesn't simplify. It's a prime number, so I'm going to leave 3 there. The 6, however, will break down into be a 2 and a 3. So I now have my prime factorization. I can rewrite that square root of 18 as the square root of 2 times 3 times 3. All this is, underneath the radical here, is the prime factorization of the number that I had underneath the radical, the radicand. Our next step is going to be to identify any pairs of numbers. These are going to signify a square factor. So I'm going to take those same numbers that I just took, the 2 times 3 times 3, and I want to see if I have any numbers that pair up. In this problem I do. I have a 3 and a 3. Those are going to pair up, and we're going to call those square factors. So now what we're going to want to do is under the radical, we're going to separate the radicand into square factors and non-square factors. So I'm going to take that square root of 2 times 3 times 3, and I'm going to split that apart. I'm going to take the ones that matched up, my 3 and my 3, and I'm going to put them together underneath their own square root symbol, 3 times 3. And then I'm going to multiply that by the one that didn't pair up. In this case, it was just a 2. And then the last step is to pull the perfect squares out and multiply them by the radical. This is now going to be our coefficient. So this is going to be where we use that process that I talked about at the very beginning. If I were to look at the square root of 3 times 3, another way to write that would be the square root of 3 squared, because 3 squared means I'm multiplying 3 times 3. because these are inverse operations, that's going to cancel each other out and just leave me with a 3 here. So that's going to be my new coefficient. Now I can't do that with the square root of 2 because I don't have anything squared here. 2 is not a perfect square. We don't have any integers that will multiply by itself to give us 2. That's actually going to be an irrational number. So we can't simplify that part since it doesn't have anything that's squared. So it has to stay as the square root of 2. So that is going to be our final answer. We're going to have 3 square roots of 2 is how we would say that. We took the factors that paired up, we took the square root of those and got rid of the radical, and then remember anything that was left up that didn't pair up is going to go underneath the radical and stay as the radicand. Alright, one more example, square root of 100x cubed. So we're going to follow that same process. We're going to first do a factor tree. So I have 100x cubed. Now 100 we can break down to be 10 times 10. We can break down 10 to be 2 times 5 and 2 times 5. Now each of those are prime numbers, so I'm going to circle them. And then when I have x cubed, that can break down to be x 3 different times. So I have a prime factorization of 2 times 2 times 5 times 5 times x times x times x. And those are all underneath the square root. So what I want to look for now is pairs. In this case, I have a pair of 2's. I have a pair of 5's, and I have a pair of x's. So what I'm going to do is, again, I'm going to pull out these square factors by themselves. So I'm going to have a square root of 2 times 2 times a square root of 5 times 5 times a square root of x times x, and then the square root of anything that didn't pair up. Now, in both of these examples, we've only had one term that didn't pair up. If we had, say, a 3 or a 7 or something else that was in there that didn't pair up, all we would need to do is to multiply those together underneath the radical. So our last step is to go ahead and simplify this. Remember, this is really the square root of 2 squared. This is really the square root of 5 squared. And this is really the square root of x squared. And then this is still just the square root of x. So I can cancel out, because these are inverse operations, the square and the square root. So what that leads me to have is 2 times 5 times x times the square root of x that's left behind here. So I'm going to multiply 2 times 5 and get 10, and 10 times x is 10x. And then I still have the square root of x underneath, and I have my answer here. Now, as you work more of these problems, what you are going to start noticing is in these problems where we're simplifying, we're going to see perfect squares occur quite a bit. And what perfect squares are numbers that have 2 integers, or well, really 1 integer, that when you multiply it times itself, you get the number you're looking for. So just as an example of some of your early perfect squares, 1 squared gives you 1, 2 squared gives you 4, 3 squared equals 9, 4 squared 16, 5 squared 25, 6 squared 36, 7 squared 49, 8 squared 64, 9 squared 81, and 10 squared is 100. So if you're simplifying and you notice these numbers at all in your simplification process, you can kind of use that as a shortcut to go ahead and pull those perfect squares out. So for example, in this problem that I just did, I had the square root of 100x cubed. If we notice, 100 is one of those perfect squares. Its perfect square is 10, because 10 times 10 is 10 squared. So when I have those perfect squares, I can go ahead and immediately pull those out front by writing its perfect square. So the perfect square of 100 is 10. And then that leaves me with the only thing I need to simplify as being the x cubed. So then I still follow the same process. X cubed is x times x times x. I still look for pairs, which I have a pair of x's. And then I have 10 times the square root of x times the square root of x. This is going to simplify to be just x, so I have 10x square roots of x, which is the same answer I got below. But I didn't have to go through all the process of the factor tree, and I had less pairs that I had to worry about losing. So pay attention to those perfect squares. That will help you simplify these a lot quicker. We did provide for you guys a list of perfect squares in the back of this packet if you look at Appendix A. Really encourage you guys to memorize those, at least up to about 15, and that will really make your lives easier in these problems. Alright, that wraps it up for this video. We do have one more video in this lesson where we're going to put videos 1 and 2 together and put it together as a final product. Alright, see you guys in that video.